All right, it's 12:59 in my world. That rounds up to 1 o'clock, so we're going to go ahead and get started. Thank you to the few of you that are here. Thanks for coming, as usual. This week we are hitting the midweek, or I should say the midterm part. So week 4, we're doing modules 7 and 8. That are 4 sections, 12, 13, 14, and 15. I think you're going to really like section 13 because it's pretty short. So it makes it a little bit nicer. So as we go through here, what is expected this week? You're going to have the 4 web work assignments, right, 12 through 15. You're going to have 2 quizzes, 1 for each module. We have 1 Excel assignment, which is histograms, and I will be putting a video up for that. I don't have it up yet, but after we finish class and I convert this video to make it usable, I will post the class video along with that Excel histogram video. And if I have a video for Project 2, which I don't think I do, but if I do, I will find it and I will post all of those videos together later, probably around 3:30 or so. You have 2 discussion boards, and then a reminder that Project 1 is due this Friday. So it's kind of a random due date for the project. Everything else in Unit 1 is past due, right? That is over. But Project 1 is due on Friday. So I know a few of you have already turned it in. High five to you. If you haven't, please do that. If you haven't started, yikes, but there is a video somewhere in one of the announcements. You can go back through and check those out to help you get started on that. As usual, feel free to shoot me an email if you have questions on that. I will be on my computer, most of the evening tonight, part of the day tomorrow, and probably about all day Friday. So if you have questions, I will be available. Projects are 20% off for every day that they are late. So if you do turn those in late, I do take partial credit for those, but that's about it. So Project 2 is also going to be assigned today, and that is due on the 18th, which is a Tuesday. So another random due date. I don't know where I came up with those due dates, but hey, makes it a little bit exciting. So mark those down, get them in your calendar, and you can go from there. So hopefully you already are almost done with Project 1. You can start Project 2, knock those both out this week, and just call it a day. That would be optimal. So I did just post an announcement about a half hour ago with all of the assignments for Unit 2. There's been some confusion with these soft due dates, hard due dates. This is my first semester trying this. But remember that everything from Unit 2, outside of the project, is due, hard due date, the day of the exam. So if you look under the latest announcement, it has everything that is due the day of the exam. So if you want to write that down or print it out or copy that, whatever, and then just kind of check those things off as you do them, and that'll make sure you have all the assignments done for that particular unit. Again, if you have any questions, you know how to find me. I think everybody who's in the class today live, you've all emailed me at least once, so high five to all of you. If you do have questions, continue to email me. You guys are doing great. So, okay, let's go ahead and get into this. Section 12, we almost should have done Section 12 last week with 10 and 11 because carbon dioxide emissions, this section is more conversions. Okay, so you are going to need your yellow sheet today, that page 245, 246. So if you have that out, that'd be great. On page 245, the front side of that, about 2/3 of the way down, you see a heading that says carbon dioxide emissions, and there are two different statements, one of them being from gas and one from electricity. So those are the 2 things that we're going to talk about in this particular section. So when we talk about gas, when you burn gas in your car, you produce 19.8 pounds of CO2 for every 1 gallon of gas you burn, right? Which to me is crazy because when you burn gas, you don't see it, you don't feel it, but 19.8 pounds of carbon dioxide is emitted into the air. So that gives us an identity ratio. Think back from sections 10 and 11. There's an identity ratio when you're dealing with carbon dioxide in gas. All right, so the key is knowing what we're dealing with. Now when we get to electricity, well, so if you have an Xbox One plugged in right now at home, and you're obviously not playing it because you're hanging out with me, or you're playing it while you hang out, in that case, really high five to you. But you are emitting 1.37 pounds of carbon dioxide into the atmosphere for every 1 kilowatt hour. And you might say, what the heck is a kilowatt hour? Well, that's a good question, and we're going to spend a little bit of time talking about that here in just a little bit. So those are the two identity ratios, right? One from electricity, one from gas, and they are located on your yellow sheet, page 245. Okay, so let's go ahead and use these and do some problems. So I use 17 gallons of gas to get to work each week. How much CO2 do I produce? All right, so some of these problems, it's almost easier to go backwards. Some of them, it's easier to start with what you're given. It kind of depends what you're talking about. So one thing, I don't know about you guys, but I'm a creature of habit, and I'm also pretty lazy when it comes down to it. I want to do things the easiest and most efficient way possible. So when I see I'm using CO2 and gasoline, as soon as I see CO2 and gas, like a trigger flies off in my head, and I know I have to use 19.8 pounds per 1 gallon of gas. I have to. That is the only way to get to CO2 from gasoline. Okay, and this is kind of working backwards, so if this confuses you, you might want to just kind of not think for a second. But the question is, how much CO2? So I know that my answer is going to have just the label of pounds. And again, this goes back to section 10 and 11. If you understood those two sections, this one shouldn't be too horrible for you. So if I want just pounds, right now pounds are in my numerator, I need to get rid of these gallons. How do I get rid of gallons if they are currently in the denominator of my red fraction? Anybody remember from sections 10 and 11? Maybe I should have asked if anybody could hear me first. Can you guys hear me? Okay, whew, people are hearing me. That's good. Multiply by 17 gallons. Yes, numerator of the blue fraction. Good, and I love the colors. Thank you. Yeah, so remember gallons, if we want them to go away, we want them to be in opposite spots. So as Nathan said, multiply by 17 gallons, and as Chrissy mentioned, put those gallons in the numerator of the blue. So that allows my gallons to cancel out numerator to denominator, and then we just multiply, right? So 17 times 19.8, we end up with 336.6 pounds of CO2. And that's how much carbon dioxide I am producing when I use 17 gallons of gas to get to work in a week. This just kind of makes you think of different things. All right. Okay, so let's do one that's a little bit different. Stop me if you have questions. My car averages 37 miles per gallon. And this all of this section does assume that you know what like MPG stands for. So if you don't get in your head, there's miles per gallon, right? So as a fraction, that would be 37 miles over 1 gallon of gas, which as an identity ratio could also be 1 gallon over 37 miles. So if I drive 400 miles each week to work, how much CO2 do I produce? Okay, well, still thinking, you're still going, let me go back to red, CO2, gasoline. So I know I have to end up with the 19.8 pounds over 1 gallon. Now, in thinking backwards, this kind of goes the same, starts the same way as we did that last problem. If I know I need to get rid of these gallons, I have to put gallons on the top. So my blue identity ratio comes from this blue statement up here, but I need gallons to be on the top. So I'm going to have 1 gallon on the top, which puts my 37 miles in the denominator. That allows my gallons to cancel out, but now I have miles in the denominator. So it's the, well, how do I get rid of miles? Well, if they're in the denominator now, you need to put them up here. So I'm going to have 400 miles over 1 divided by 37 miles Well, now those miles cancel out, and now you can see my only label is pounds. So just like in sections 10 and 11, you really have to let your labels guide you. All right, now let's go for a numerical answer. We got numbers in the top and the bottom here. How many pounds of CO2 do we produce here? And you can round to the nearest whole pound if you'd like. 214, fantastic, good. Nathan took it all the way out. 214-ish pounds. Yep, remember, divide by in the bottom, multiply those in the top. Good. All right, so there's your basic run-through of gasoline. And, of course, in your packet, there's a lot more examples of gasoline, but I think I might have one more later if we need it. All right, so we are moving on to electricity. Now, with electricity, notice I have page 102 written up here. So if you have your packets handy, and you could open that up to 102, I would greatly appreciate it. You're probably, yeah, I think you do. I think you do need page 102 and 103 for web work. 102 and 103 give some basic appliances and their watt usage. That's W-A-T-T, watts. So when you plug something in, right, it uses a certain number of watts. And that's how we calculate then kilowatts, kilowatt hours, and figure out how much CO2 you're going to produce. You can also use that to figure out how much this stuff is going to cost you. Section 12 is what Project 2 is based off of. I like Project 2. I think it's interesting. I always have a lot of fun reading those. So we'll get to that here in a bit. So here, number 3, I use my microwave 6 hours a month. Yeah, that's probably pretty accurate. How much CO2 do I produce each month? All right, so from page 102, let's go ahead and find our microwave. That would be under the kitchen appliances. How many watts does a microwave use? $1,500. Fantastic. Okay, and so a microwave uses 1,500 watts. Now, going back to kind of our thought, now we're talking about CO2 and an appliance. An appliance is not gasoline, that's electricity. So I know that I'm going to be using 1.37 pounds per 1 kilowatt hour, right? This is the conversion for CO2 with electricity. So the goal now, when you're working backwards, we have to get rid of kilowatt hours. Well, we're going to do that in 2 steps. We're going to have kilowatts and we're going to have hours. Okay, so first things first, I'm going to go back up here to this orange piece. 1,500 watts. Think back to our metric conversions. Watts is like a unit. It's like liters, meters, and grams. If I want to go from watts to kilowatts, how do I do that? From units to kilos. How do we do that? 3 places to the left. Very good. So recall that from your metric days. 1, 2, 3. That means this is the same as 1.5 kilowatts. So that's what I'm going to start with, 1.5 kWs. So those kilowatts cancel out with kilowatts. But now I still have these hours down here. Based off this problem, what can you tell me about hours? Nathan, you also could divide up that 1,500 by 1,000. That's absolutely correct mathematically. Yep. Depending if you watch some of my videos, I do start them like that. I don't always do the counting method. How many hours are we using this microwave for? 6, exactly. So I'm going to have 6 hours. So because I'm using this for 6 hours, hours canceled out with hours. Now you can see all of my labels down here in the denominator are gone, and I'm just left with pounds. So I multiply straight across, and I end up with roughly 12.33 pounds of CO2 from using my microwave 6 hours a month. Okay, so your goal in your numerator, right, because if you think about how the goal, you need kilowatts and you need hours in order to then transfer to pounds. It doesn't matter how you get there, but those are the 2 things that you need to go to pounds. All right, let's do another one of those. Let's have you guys try one of those. My electric clothes dryer is used 3 hours a week. So how much do I produce in a year? So this is a little bit different, but I want to see if you guys can do this. So go ahead and look at page 102 to figure out how many watts your clothes dryer uses, and we'll go from there. Nathan, that is not the answer that I got. Yep, Christy, that's the answer that I got. So let's start with watts, right? How many watts does an electric clothes dryer use? $3,400. And don't freak out about, if you look at the wrong thing, that happens here. When it comes to exam time, the number of watts will be in the problem. So you don't have to go find it. They give you the watts, which, I wish we'd do that in web work, but we don't. So I make you do it here. Okay, so if we have watts, and then we want to go to kilowatts, right? We go 3 places left. So we have 3.4 kilowatts. All right, how many hours are we doing this for? Let's talk hours. 3 hours a week. So it's 3 hours in 1 week, but you're not only doing it for a week. We want to do it for a year. How many weeks are in a year? 52 weeks are in 1 year. And you don't necessarily have to write all this out. I just want to show you where my numbers are coming from, right? There are 52 weeks in a year. So you got to take that 3 hours a week, multiply it by 52 weeks in a year, and now we have kilowatt hours multiplied by 1.37 pounds per 1 kilowatt hour. Give me a different color. Kilowatts cancels out with kilowatts. Hours cancels out with hours. Multiply straight across, and you get Christy's answer of 726.65 pounds. Okay. How are we doing so far with CO2 emissions? Pretty good. All right, I want to do one more problem. I've got a couple more on here, but sometimes I feel like I do too many. So you guys can let me know if we need to do more. But in number 5, we're going to utilize page 103. 103 is what we call vampire energies, or energy vampires. It's when things are plugged in but they're not being used. So like right now, I live alone. So right now my apartment is completely dark. Every light is off. It's supposed to be. Nothing is on. However, everything is plugged in because I don't unplug things when I'm not there. So even though I'm not there and nothing is on, it's still costing me money. Or you go on vacation for a month and you're not even home, you're still going to have an electricity bill because all of those things that you have plugged in are still drawing energy and you still pay for them and they still produce CO2. Now, it's all less, right? If you look at the wattages on page 103, they are considerably smaller than the wattages on page 102 because 102 assumes that you are using them at that time. So we're looking at a DVD player. It's on standby mode, approximately 20 hours a day. That's assuming I watch 4 hours of movie a day, but hey, whatever. So how much CO2 is produced in a month when I'm not using it? We're going to assume there's 30 days in a month. So first things first, based on page 103, what is the wattages of a DVD player on standby? Good, 1.55, and that's watts. Okay, how do I change that watts to kilowatts? Left 3 places, so 1, 2, 3. Notice I have 2 empty humps, so I have zeros. So this gives me 0.00155 kilowatts. Okay, so this is where I'm doing my problem. All right, now let's talk about hours. How many hours is my DVD player on? And we're talking standby mode. right? We're not using it. We don't care how much I'm using it. We're talking about not using it. How much am I not using my DVD player in a month? 20 hours a day for how many days? 20 hours per day, and we're doing that for 30 days. Yep. So you can do this 20 hours times 30 days because that will go ahead and let your days cancel out. Or you can do what Jessica did and just say, well, 20 hours a day for 30 days, that's 600 total hours. Either way, you get the same thing. Now we have kilowatt hours. So again, we're talking about electricity, 1.37 pounds per 1 kilowatt hour. Kilowatt cancels out with kilowatts, hours cancels out with hours, and I have an answer of what? Anybody got those multiplied together? Excellent. Thanks, Nathan. 1.2741 pounds. And of course, you want to make sure you're paying attention to what you're rounding. Some of you lost points on your first exam because you simply did not read the directions for rounding. And I can give you partial credit, but I can't give you all the credit because you didn't follow the directions. So that's something to be aware of in the future. Okay. Questions on CO2 emissions? Okay, if you decide you want to see more of those later, we can come back. I got a couple more, but I'm not going to bore you. So that's section 12. And of course, watching the videos that go with the packet will give you some more in-depth problems and discussion. All right, section 13. This is the only slide I have for section 13, bar graphs and histograms. I honestly believe in my heart of hearts that if I gave you guys a bunch of numbers and said make a bar graph out of this, you could. I honestly believe that because we all have an idea of what they're supposed to look like and we have a general idea of how to do that. It just comes with being an adult, I think, that you can think through that problem. So I'm not going to bore you too much with this. However, there are some key things that we need to discuss. And one of those is the difference between a bar graph and a histogram. So a histogram is a type of bar graph, but there are some differences. So a bar graph uses what we call categorical data. So categorical would be things like eye color, blue, brown, green, hazel. Those are categorical. They're not numbers, right? They're things. Types of cars, that's categorical. Grades in a class, categorical. Anything that you can categorize would become a bar graph. And with bars, a bar graph, the bars do not touch. Right? So when you make a bar graph, let's make this look right, you have bars and they don't touch, right? This would be a bar graph. And the reason they don't touch, think about if you're talking about eye color. When bars touch, it means that there is a fluidity from one to the next. Well, if we have blue eyes and brown eyes next to each other, that means at some point there's this fluidity from brown to blue. No, I always have blue eyes. That doesn't run naturally to brown. They are distinct, separate pieces. So categorical data generally is distinct and separate, and that is why the bars are distinct and separate. Now, with a histogram, you probably see where this is going. Histogram generally deals with numerical data, and even more so than that is continuous data, because there is numerical data that is categorical. I might add one more slide, otherwise I think I might be confusing you. But here's the deal with these, the bars touch. Okay, so in a histogram, bars touch. So when you create the bars, one side is just part of the next one. And examples of this would be like age. There's not really a distinct separation between when you are 35 and when you're 36. Yes, on your birthday, you turn 36, but it's not like a boom, it happens, right? It's gradual. There are 364 days between your 35th and your 36th birthday. There's all of those in betweens. So when you're looking at numbers, 1 to 2. If you can have fractions in between or decimals in between, you have continuous data. So like the amount of water in my water bottle, I could have 1 ounce or 2 ounces, or I could have 1.5. So because I can have all those decimals in between, that's continuous. An example of a numerical that is categorical would be like runs scored in a baseball game. So you can score 0 runs or 1 run or 2 runs or 3, but you can't score 1.5. That doesn't work. They're distinct, right? This is 1 run, this is 2 runs, this is 3, this is 4. So because there's not the ability to have decimals in between, you have to have distinct bars. So hopefully that kind of makes sense. I highly recommend, if you're like, I can do bar graphs, I don't need to watch any videos, blah, 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 high five. Highly recommend you watch the video that goes with page 111. If nothing else, just watch that one. It's probably the second or third video of the bar graphs. But it deals with frequency tables, making a frequency table, using that to create a histogram, and then how you can use that histogram to find other types of mathematical things. Okay, so please go ahead, and if you can't find which video to watch, shoot me an email. I'll send it to you. That's how much I want you to watch it. All right, that's section 13. Anybody have any questions on my basic discussion of that? Going once, going twice. Sold. All right, section 14 jumps into the normal distribution. I love sections 14 and 15. They're two of my favorites in this entire packet. Here's the deal with the normal distribution, and this is where drawing with a mouse can get a little bit ugly. Pretend that's a straight line and pretend that's symmetrical. That's not too bad. So the normal distribution basically says that 100% of our data will fall underneath this beautiful curved line. Okay, so it's a way to represent our data. 100% of our data falls underneath the curve. Another thing about this, it is symmetrical. So you draw a line down the middle, and if you understand the term of symmetrical, the left side and the right side are identical. I know it doesn't look like it in my picture because I can't draw, but there it is. The last thing that I want to talk about on this particular page is that the area under the curve, so any area under the curve, refers to probability. So we are going to be able to answer some probability questions based off of what space under the curve. If we're looking at just this little space, what's the probability that something will fall in that spot? And that's what we can do based off of the normal distribution. Okay. All right, now dealing with what we're going to get to, erase that. Let me redraw myself a beautiful, actually I want two little ones. All right, so these are both considered normal curves. Obviously, one is prettier than the other, but yeah, maybe not. Okay, so when we have the normal distribution and we have our line of symmetry, the mean falls directly in the middle. That is part of the dealio with a normal distribution. Remember the mean, add them all up, divide by how many you are, there's your mean. And then we have what's called the standard deviation, and we're going to get into that more in just a minute. But standard deviation is noted by sigma, which is a little curly Q, right? Standard deviation. And the standard deviation tells you how far you are from the mean. That's the basic definition of standard deviation. How far are you from the mean? So you can see in this case, let me change colors for effect, and we're going to get more into this. Here, the standard deviations are pretty close to the mean. There's really little. So this one has a small standard deviation. High and tight is what I call it, because you can see how this is a taller and it's pretty skinny. High and tight means you have a small standard deviation. If you look at our second picture, again, the mean is in the middle, but now our standard deviation, they're more spread out. See how it's bigger. So this one will have a big standard deviation. So if your graphic is short and fat, your standard deviation is going to be bigger than if it was high and tight, tall and skinny. Because when you're tall and skinny, more of your data is clustered around the mean. The more of it that is clustered around the mean, the smaller your standard deviation is going to be. So, okay, let's get into something a little bit more concrete than just me drawing pictures. The empirical rule. Okay, so basically with the normal distribution, there are a couple different ways that you can use the normal distribution to predict probabilities, and one of them is with the empirical rule. The empirical rule is great for certain problems and it sucks for other ones. So it really kind of depends what we're going on. I'm going to do a 2-minute colored pictorial representation here, and if it makes no sense to you, you can go ahead and ask now, or there is a video in that spreadsheet that I sent you a while ago that is simply titled The Empirical Rule, and I go over this exactly what I'm going to do here in that video, so you can watch it again and again. It's like 2.5 minutes long. Okay, so the empirical rule is basically a way to talk about the probabilities within the normal distribution. So I'm going to use a mean of 70 and a standard deviation of 5. Because I don't know about you guys, but I'm a concrete person. I need numbers. If you use a bunch of symbols to tell me about math, it just doesn't make sense to me. I need to see numbers to see how they add, subtract, multiply, divide. I need to see how those things all work before I can really, jump in and see what's happening. So with the normal distribution, based off of what I said earlier, what value is associated with this red line? Do any of you remember from that last page? What goes in the middle? The mean. Exactly. So in this particular example that I made up, the mean is going to be 70. So this value will have a numerical value of 70. Okay, so let's use blue as our next color out. The empirical rule. Some people call the empirical rule the 68, 95, 99.7 rule. And that's because the empirical rule estimates the percentage of data that falls within 1, 2, and 3 standard deviations of the mean. So if we look at 1 standard deviation away, that's these blue lines, 1 standard deviation away represents 68% of our data. So think about 1 standard deviation. If our standard deviation is 5, if I started at 70 right here and I'm going to go 1 standard deviation to the right, is my number going to get bigger or smaller, and by how much? Right, my red line is 70. I want to go 1 standard deviation to the right. What's that right blue line value going to be? It's definitely going to be bigger. Bigger by 5. Perfect. Yep, it's going to be 75 because standard deviation is 5. So if it's getting bigger, because we're going to think of like a number line, if we're getting bigger by 1 standard deviation, we're going to add 5. Now, use that same thought process. If I'm going to go to the left of my mean, we're going 1 standard deviation to the left. What is that value on the left going to be, the left blue line? 65. Exactly. So we're going by standard deviations. So those are the values. Now, 68% of our data falls between these two values. Okay, so 68%. I'm going to run out of space, but it'll be okay. So we know that that red line cuts this thing exactly in half, right? It's symmetrical. So if I have 68% cut exactly in half, what percent is in each spot? 68% cut exactly in half. Exactly, Samantha, 34. So if I take 68, excuse me, and divide by 2, I get 34%. Now, what this tells us is that 34% of our data would fall between 65 and 70, or 34% of our data would fall between 70 and 75. All right, so if these were test scores, I could say 34% of students score between a 70 and a 75 on their exam. That's what this tells us. Okay, now we got to continue. So 95 is the second number, which means it's 2 standard deviations away. So if I'm looking at the right pink line, I'm going to go another standard deviation to the right. What is the value of the right pink line? 80. Fantastic, because we just another standard deviation. And on the left, my value would be 60. Good. Okay, so mathematically, by the empirical rule, 95% of our data falls between these two pink lines. Well, if you recall, we already have 68% accounted for in the blue. So how much is left unaccounted for? 95 minus the 68 we already talked about leaves us how much? 27. Exactly. So these two pink spots share 27%. And again, this is symmetrical, so it's got to be even. So if I divide by 2, what percent is in each spot? 13.5. Okay. And I'm sure you know where we're going with this for the last one here. 99.7 is the third standard deviation. So again, we add and subtract. And so that means 99.7% of our data is between these two green lines. Well, if you recall, 95% is from pink to pink. That means 4.7% of my data is left. Divide by 2, and I have 2.35% in each of my green spots. So I could say 2.35% of my students will score between a 55 and a 60, right? This is an estimate. Now, the entire curve represents all of the data, but this only accounts for 99.7. That means we have 0.3% left in what we call the two tails. So if I take 0.3 and divide it by 2, I have 0.15% in each of my tails. 0.15%. And that is where these numbers come from. Okay, because you're going to be expected to use these numbers, and I think it's a whole lot easier to use them if you know where they come from. So this is where the 68, 95, 99.7 rule comes from. So you can now say, what percent of students score between a 70 and an 80? Well, here's 70 and here's 80. So if I want between that, I just look at the two numbers that are between. So I would take 34 plus 13.5 and say 47.5% of students score between a 70 and an 80, right? And that's how we can use the empirical rule. So the empirical rule is great if your number falls on one of these 7 numbers. If it doesn't, I guess you're just out of luck. So if I said, what's the probability of a student scoring higher than a 67, I don't know that based off the empirical rule. I can give you higher than 65 or higher than 70, but with the empirical rule, we are limited to just those values. Okay. All right, we're going to do a problem with the empirical rule now. So basically, we're going to recreate this again. You will notice on page 246 in your packet, which is the other side of your formula sheet. We're going to use that in just a minute. You do not have this empirical rule on your formula sheet, which means you do not have to use these percents anywhere on the exam. You don't have to have them memorized. You do need to understand the concept of 68, 95, 99.7 of what that means, right? 1, 2, 3 standard deviations away. But when it comes to all of these little percentages inside, you will not need them for an exam. If you have them memorized and you want to utilize them, you can, but you totally don't have to. All right, enough chatting. Let's do a math problem. The average miles per gallon in a luxury car is 29 with a standard deviation of 3, and this is completely and totally made up. So we're going to do a 5-part problem here. So the first thing that we're going to do is we're going to draw the normal distribution curve, basically what we just did, but with our numbers. So using 29 and 3 instead of 70 and 5. And then we're going to go ahead and do some probability problems. Okay, so I highly recommend that you draw this out. Hopefully you have scrap paper in front of you. It'll make your life a little bit easier if you draw it all out. So let's go ahead and go to the first page. So the normal distribution. Hopefully I'm going to just give you guys a minute and just give me a yes in the chat box if you when you have your curve finished. So you want your mean in the middle, and then your standard deviations working their way out. And Yarley's on it. All right, so that's 5 of the 7. It's pretty good. Okay, so let's go numbers. All right, 29 in the middle. Moving to the right, you add. So well, we got 32, 35, 38. And to the left, we've got 26, 23, and 20. Excellent. That you should be able to do. Okay, so you got your percents in there. Great. We have those from the previous one. These percents never change. That's the beauty of the empirical rule, is that once you understand where they come from, your life is pretty easy. Okay, so that's what we're going to use. Hopefully you guys have that all written down, because now we're going to answer the questions, and I'm going to just, oh, balls. Yeah, I can leave that up there. This will be great. Okay. I'm still working on this whole thing. All right, so any questions on drawing the normal curve with the labels? Everybody good? Of course you are. You guys are rock stars. All right, so part B and C we're going to kind of do together. What is the probability that a car gets less than 23 miles per gallon? So I'm going to use green for this one. Less. Okay. Less than. Which direction? So here's 23 right here. Which direction, left or right, tells me less? Left. Samantha had that answer before I even finished talking. Yeah, less is to the left, and that makes sense because as you go left you get to 20. That is a smaller number. So if you want less than 23, you simply add everything to the left of that line. So I would take 0.15 plus 2.35, and that gives me what percent? 2.5. So part B has an answer of 2.5%, right? Less than 2.5%. Great. Now, in part C, which is similar, it says what's probability a car gets more than 23? Well, more is everything on this side, right? It gets bigger. There are two ways to find that. One way is to add up all those numbers, and that's great, but you know what? When I add up 6 numbers together, I have a pretty high probability of maybe messing it up. What's another way I can find the area to the right without adding all of those numbers together? Okay, Nathan, you're super on the right track. Subtract 2.5 from what? From 100. No, from 100. So remember, from the very, very first slide of this section, I talked about the total area under the curve, right? The total area under this curve is 100%. So if we start with 100, that's all of it, and we know that to the left is 2.5%, well, then that leaves us with 97.5%, which is everything on the right. So if you The left and the right together have to add up to 100% because the left and the right together make up everything, and everything is 100%. So if you already know area to the left, you can find area to the right simply by subtracting from 100. Okay, does that make sense? Because we're going to need that moving on to section 15 here in about 3 minutes. The whole concept that the left side and the right side together add up to 100%. That's the concept that we're going to need to have with us. Okay, so part D says, what is probability that we get between 20 and 32? Let me change colors. So 20, oh, dang it. I keep forgetting to hit my pen button. So 20 is here, 32 is here. So if you're going between those, how do we find the area between those two values? Between 20 and 32. I'm going to add all those together, right? Yeah. So 2.35 plus 13.5 plus 34 plus 34. That's all of these values between 20 and 35. So we would end up with 83.85% will fall between 20 and 32. If you have yourself a visual, it makes these problems a whole lot easier because you can, draw all over them just like I did. If you're trying to do everything in your head, it's pretty hard. Pretty hard. Okay. And the last one says, how likely? Now, when it says how likely, that's another way of saying probability. Okay? So when it says how likely, you want to give a percent answer. So how likely is it that a car gets more than 38 miles per gallon? Well, 38 is here. More than that is to the right. There's only one number to the right, so Jessica's absolutely right. The answer to this one is 0.15%. So how likely is it? Well, it's not very likely. It's 0.15%. So, super small. Super small. All right, so hopefully you can see the benefits of the empirical rule, that it's clear cut, you can see exactly, but there's also limitations, right? We only can use the 7 numbers given. You can't use 22 or 27 or 38. No, you can't use 39. You can't use any numbers that aren't listed on the horizontal axis, and that's troubling. So that leads us then to section 15. Okay. Once you understand the empirical rule, section 15, I need to erase this now, z-scores. So we see the beauty of the empirical rule and how we can use it, but you also see the limitations that it gives you. It only allows you to find probability around 7 numbers. So the idea of z-scores allow you to find the probability for all the numbers, anything that you can think of. So basically a z-score is a way to standardize numbers to make them deal with the mean. What that means, I don't know, I feel like I'm just not making any sense, which is possible. So if a z-score is 2, that means this is 2 standard deviations above the mean. And I know that it's above the mean because this number is positive. A positive z-score implies that it's bigger than the mean. If I have a z-score of negative 1.7, that means this is 1.7 standard deviations below the mean. I know it's below because it's negative. Any negative z-scores fall to the left of the mean. With this, when we're talking about z-scores, it kind of standardizes. So when we're talking about our normal distribution with z-scores, the mean is 0. And then anything, right, a z-score of 2, here's a z-score of 1, z-score of 2, -1, -2. And that means that this -1.7 would fall about right here, -1.7. So with z-scores, you can have anything, but it standardizes everything so that you have a mean of 0. That means anything positive is to the right of the mean and anything negative is to the left of the mean. That's kind of the basic, what is a z-score. This is where page 246, the table at the top of that page, is going to come in handy. That's how we're going to find probability using z-scores. There is a formula. So the first things first, the formula is z equals x minus mu over sigma. And if you don't know what those mean, that can be troublesome for you. So to put that in people words, that's value minus the mean over the standard deviation. So generally in a problem, you are going to be given the mean and the standard deviation, and then you're going to say, Billy scored a 42. What was his z-score? Well, whatever Billy scored or whatever number you have, whatever it is you're talking about, that's the value. Okay, so let's pretend, I want you to pull out, we're going to look at the table now. I want you to pull out your formula sheet, page 246. Because before we get into an actual problem, I want to do at least one of these. All right, so if you all have page 246 in front of you, we have a z-score of 0.35. That means you are 0.35 standard deviations above the mean. Now, the table on page 246 and every z-score table you will ever encounter in any statistics books anytime in your life, the table always gives you area to the left. Oops, I can't spell. Always. That's an F. So if I'm looking at the table at 0.35, it's going to give me the area to the left of 0.35. What is the area to the left of 0.35? Use your table. Find 0.35 in there. What probability is associated with that? Excellent. So 0.6368. Not 3.5, Jessica, 0.35. Decimal point difference. So 0.6368 is 0.35. That's the area to the left of 0.35. Okay, now thinking back to what we did just a little bit ago, how would I find the area to the right of 0.35? If I know the area to the left is 0.6368, how do I find area to the right? What mathematical operation are we going to use? Subtract from 1. No, Jessica, the z-score is only used to identify what number you're using in the table. It's not used as any part of the probability. Remember that the entire curve is 100%. Well, this number, 0.6368, is a decimal. So 100% as a decimal is 1. So if I take 1 minus 0.6368, that gives me the area to the right, which is 0.3632. If you add this green number and this pink number together, they will add up to 1, because together the left side and the right side equal the entire thing, which is 1 or 100%. Okay. Does that make sense to everybody where these numbers are coming from? I hope so. And remember, I'm just going to draw a little one up here. Remember that the mean that falls directly in the middle has a z-score of 0, and it cuts it directly in half. So when you are looking at your mean or a z-score of 0, you're going to have 50% on each side. If you look at 0, a z-score of 0 on that sheet, it shows probability 0.5. So when you're looking at 0.35 and you can recognize where that falls, well, that falls on this side. All of this then, the red half and a little bit of green, that has to be bigger than 50%, right? But it is, it's 63.68. So the more you can kind of make sense of this, of how it all fits together, the easier the problems are, because you can kind of think through them a little bit. All right, let's do a problem. Let's also erase some of these drawings. Average calories burnt at the gym is 460 with a standard deviation of 35. First things first. And Nathan, yes, that is true, and that's always true because you are symmetrical. We want to find the z-score of somebody who burnt 510 calories. Okay. You're welcome. All right, so remember the z-score formula. X minus mean, so the value minus the mean divided by the standard deviation. Sometimes the mean and the standard deviation are the easiest ones to find, right? It says average calories burnt is 460. Well, the average is the mean. So I know that 460 is going to go in here because I'm subtracting the mean with a standard deviation of 35. Well, the standard deviation goes in the denominator. Then when it says, what's the z-score of somebody who burnt 510 calories? Well, those 510s, that's the value that's in question. So I'm going to do this. Depending on your calculator, or if you're using Excel or whatever, you might need to put your numerator in parentheses. Or you want to subtract the numerator before you hit divide. Either way, if you want to plug it all into your calculator at the same time, then you want to put the numbers in parentheses first. Either way, if you get 50 divided by 35, what is the z-score of this problem? All right, so approximately 1.43. Now, if you look at, okay, let me move on to the next page first. Because we're going to do part B here, which is what is the probability of somebody who burns less than 510 calories? So if 510 calories leads us to a z-score of 1.43, and that's positive 1.43, so it's going to be on the right side of the mean, right? This is z equals 1.43. Now, if I want to talk about probability of burning less than that, which direction am I looking, right or left? If we're talking about less than 510 calories. Left, very good. So I'm looking for this probability. We found a z-score, that's what you need to find probability. But when you look at your yellow sheet, what's wrong? Do you have 1.43 on your yellow sheet? No is the correct answer. We have a very, very limited table. In a normal stats book, a z-score table is 2 or 3 pages long, depending on how many digits they go out. Most of them are 2 pages. So yeah, Jessica's absolutely correct. You're going to have to round. So instead of 1.43, we're just going to use 1.4 because that's the closest one. So if I use 1.4, what is the area to the left of the z-score of 1.4? Very good, 0.9192. So there's a 91.92% chance that somebody burns less than 510 calories at the gym. That's what this tells us based off of this data. And moving on to part C, what's the probability that somebody burns more than 510 calories? Well, again, remember, 510 calories correlates to a z-score of 1.4. So this works, right, because this is also representing 510 calories. So if I want more than 510 calories, that's telling me more is on the right. How do I find this green area here on the right? Very good. Again, we're going to take from 100%, but 100% as a decimal is just 1. Since these are decimals, we want to change that to a decimal. 1 minus 0.9192 gives us the 0.0808. Yep. If you like percents better, I mean, you can have 100% and then subtract 91.92%, and that gives you 8.08%. You just have to make sure that you move your decimal and change that to a percent also. Okay. All right, let's, do you guys want to do more examples of this, or do you feel like you understand what this is, at least to get you started, and you can watch videos to go? It's 2 o'clock. I want to respect your time, but if you want to do more, I have more available. Nathan's good. Christy's good. Charlie's good. Okay. There are, obviously there are videos to go with the packet. I do recommend you watch some of those. Check out Project 2. It goes along with Section 12, located within Module 7. If you have questions on that, get those to me early so that you're not stressing out before the due date. If you haven't finished Project 1 yet, it's due on Friday, so make sure you get that going. Any other questions? Otherwise, I think there's nothing else new. Everything else is just more practice with this. So, any other questions for the good of the cause before you guys go out and change the world? All right. If you do, I'll stick around for a little bit. If you have questions, if you don't have questions, feel free to go and, make some magic happen. Thanks for coming. Good luck working on your math and anything else you're doing, and have a good one. Thanks, guys.
Hey, Becky. I have a couple questions over Section 11.
Okay.
That have me stumped. Sorry to go to a complete 360 from what we were.
No, you're good. You're good. Let me see if I can figure out how to get out of. Do you want to look at your web work, right?
Yes, ma'am.
Okay. So let me. Are you okay if I keep recording this so everybody else can learn from these two?
Yeah, that's fine.
Okay. So let me. You can say no. It's okay. Where are you at? Okay, so Section 11.
Yeah, I've been stuck. It's just questions 11 through 15. For some reason, I believe I had the setup right, but it's still giving me incorrect. I don't know how I'm doing it wrong, but apparently I'm doing something wrong.
Okay, so you're in meters, and you need to go to centimeters in this one. Okay, so think about, we're talking metrics here. So if you recall back, meters is in the middle, and then there's hecto, then cena, then, nope, that's a D. That's deci, right? So to go from meters to centimeters, we have to go right 2 places, right?
Okay, yep.
You with me? So
yep.
if I start with 1.7 square meters, square implies that we need to do everything twice. So if I need to go to the right 2 places, I'm going to go to the right 2 places. That's once, but I need to do it twice. So I've got to go to the right 2 places again. Do you see what I'm saying? These all become zeros, and so your answer...
Because of the square.
Yes.
Right. Okay.
So
that's where I was screwing up.
1,000 square centimeters. So when you're doing metric conversions, if this says square, you have to do it twice. You just, however many spots you're moving the decimal, you're going to do it 2 times.
Okay. Okay, yeah, because I kept going back and watching the videos, and I was like, what am I doing wrong here? Because I had it all set up to where I did meters to yards, and then foot for number 11, and then yards to inches, or feet to inches is what I kept doing, the conversions for that.
Oh, so yeah, you're working way too hard on that one.
Yeah, yeah.
I mean, you technically should still get the same answer if you do the math right, but that's a lot of steps to keep straight. Yeah.
Yeah, and that's probably where I just kept screwing up.
Yeah.
Okay. All right, and that's pretty much for the questions 11 through 15. That's the same idea.
Well, anytime you're dealing with square units, so like in number 12 here, you got a 24-foot by 19-foot kitchen. When you get to the store, they're in square meters. So you need basically, and you can do this 2 ways. Because they give you 2 different units, these are, both feet, you can change these to meters and then change this one to meters and then multiply them to get your square meters. Or you can multiply 24 by 19, which gives you square feet, and then change square feet to square meters. Right? You'd first have to go to square yards and then have to go to meters. So so you'd have to do all of those conversions twice. You're basically doing the same thing. It just depends which order you want to do it in.
Okay, so my math is just getting screwed up somewhere because I did that on number 12. I guess my math just got screwed up.
Which way did you do? Option 1 or option 2?
I did both. Because one, I plugged it in one way and it was wrong. I plugged it in the other way, it was wrong. So I was like, okay, well, what did I do wrong?
Right.
So yeah, no, when I set it up, I did the 24 feet, and I turned that into yards, and then the yards to meters, and I got 7.3152 meters from the 24 feet to meters.
Okay, so your first step was to divide by 3.
Yep, by 3 feet.
So then you multiplied by 0.9144, and you got 7.3152. Yeah, I agree.
Okay, and I did the same thing for 19 feet. I switched it to meters, and I got 5.7912 meters.
Okay, and then you multiplied those together, right?
Yeah. Did I multiply or did I just add them?
Oh, here's your issue. Read your directions underneath. Express your answer rounded up to the nearest square meter. So 42, that's rounding appropriately. You rounded according to math rules, but the directions say round up to the nearest meter. Because if you're covering your floor, think about this. So when I multiplied, and I'm sure you multiplied with you got like 42.36, right? So if you need 42.36 to cover your floor and you only order 42, you've got 0.36 square meters not being covered.
Okay.
So you have to round up no matter where your number is so that you can make sure that you cover your entire floor.
Okay, so it would have been rounded up to 43.
Exactly. So yeah, your math there was fine. You just didn't follow directions.
Of course I didn't. Okay, thanks.
I mean, that's a positive because at least that's an easy fix.
Yeah, that's true. That's true. Okay, and I think that's all I have for that section.
Okay.
Because everything else, it was clicking. It's just for those problems. I was like, what the heck is going on here? Why am I doing this wrong?
As you go through them and you try them again and you're not figuring them out, let me know. 13's got a hint with it. That's nice. So that means there's a video that goes with that one. Yeah.
Oh, okay.
I don't know how.
Yeah, I don't know.
Yeah, you have, after you get them wrong 3 times, so like you can see that problem 13 you only got wrong once. After you get them wrong 3 times, then those hints will show up. They don't show up at the very beginning. You have to get it wrong 3 times first, and that's where it says that right here.
Right. Okay. Yeah, well, no, I think I was just getting discouraged because I kept getting 11 wrong, 12 wrong, and then finally 13 I just kept getting wrong or I got it wrong once, and I was like, you know what?
Time for a break.
Cashing in the chips here. I don't know what's going on.
Yeah. So, no, I think your math is okay. I think, that last one you just didn't follow the directions. So,
Okay.
Yeah.
Alrighty. Okay, well, that's all I have, Becky. Thank you.
Yep, no problem. Talk to you later.
All right. All right, yep, take care.
Yep, bye.
Bye.